Now that we understand hybridization states, let's do a couple of examples. All right? And so we're going to identify the hybridization states and predict the geometries for all the atoms in this molecule, except for hydrogen. And so let's start with this carbon right here. And so the fast way of identifying a hybridization state is to say, okay, that carbon has a double bond to it. Therefore, it must be sp2 hybridized. And if it's sp2 hybridized, we know the geometry around that carbon must be trigonal planar, with bond angles approximately 120 degrees. This carbon over here, right, is also has a double bond to it, so it's also sp2 hybridized with trigonal planar geometry. All right, let's move to this carbon right here. So that carbon has only single bonds around it, and the fast way of doing it is if you see all single bonds, it must be sp3 hybridized. And if that carbon is sp3 hybridized, we know the geometry is tetrahedral. Right, so tetrahedral geometry with an ideal bond angles of 109.5 degrees around that carbon. All right, let's move over to this carbon right here. So this carbon has a triple bond on the right side of it, and so the fast way of doing this is if it has a triple bond, it must be sp hybridized here. So sp hybridized, and therefore the geometry would be linear, right, with a bond angle of 180 degrees. And same with this carbon. This carbon has a triple bond to it, so it also must be sp hybridized with linear geometry. And so that's why I drew it this way, so it's linear around those two carbons here. Let's go ahead and count up the total number of sigma and pi bonds for this. So that's also something we talked about in the previous videos here. So first let's count out the number of sigma bonds. All right, so let's go back over to start with this carbon here. So here's a sigma bond to that carbon. Here's a sigma bond to that carbon. We know that in a double bond, one of those bonds is a sigma bond, and one of those bonds is a pi bond. So let me go ahead and also draw on our pi bonds in red. So I already colored the sigma bond blue, and so let's say this one is the pi bond. All right, let's continue assigning all of our bonds here. So I know this single bond is a sigma bond. I know this single bond is a sigma bond, right? So all of these single bonds here are sigma. When I get to the triple bond, I know one of those is a sigma bond, and two of those are pi bonds, right? So two of those are pi bonds here. And then finally, I have one more bond. It's a single bond, so I know that it is a sigma bond here. And if you count up all of those sigma bonds, right, you should get 10. So let's do that really quickly. So you get, let me go ahead and change colors here. So you get 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have 10 sigma bonds total. And in terms of pi bonds, we had 3 pi bonds. So 3 pi bonds for this molecule. You can also find hybridization states using a steric number. So let's go ahead and do that really quickly. So let's go back to this carbon, and let's find the hybridization state of that carbon using steric number. So let's use green for this. So steric number is equal to the number of sigma bonds plus lone pairs of electrons. Right, so 1, 2, 3 sigma bonds around that carbon, so 3 plus 0 gives me a steric number of 3. Therefore, I need 3 hybrid orbitals, and sp2 hybridization gives me 3 hybrid orbitals. All right, if I wanted to do for this carbon, I would have 1, 2, 3, 4. Right, so the steric number would be equal to 4 sigma bonds and 0 lone pairs of electrons, giving me a total of 4 for my steric number. So I need 4 hybrid orbitals. I have 4 sp3 hybridized orbitals at that carbon. And then finally, let's do it for this carbon right here. So using steric number. Steric number is equal to number of sigma bonds plus numbers of lone pairs of electrons. So there are 2 sigma bonds around that carbon, 0 lone pairs of electrons, steric number of 2. Means I need 2 hybridized orbitals, and an sp hybridization, that's what you get. You get 2 sp hybridized orbitals like that. All right, let's move on to another example. Let's do a similar analysis. And before we do, notice I excluded hydrogen here, and that's because hydrogen is only bonded to one other atom, so there's no real geometry to talk about. All right, let's move on to this example. So this molecule is diethyl ether, And let's start with this carbon right here. So the hybridization state. Right? Well, the fast way of doing it is to notice that there are only single bonds around that carbon, right? Only sigma bonds. And so therefore we know that carbon is sp3 hybridized with tetrahedral geometry. So sp3 hybridized tetrahedral geometry. All right, let's look at this carbon right here. It's the exact same situation, right? Only sigma or single bonds around it. So this carbon is also sp3 hybridized, right? And so therefore tetrahedral geometry. Let's next look at the oxygen here. So if I wanted to figure out the hybridization and the geometry of this oxygen, steric number is useful here. So let's go ahead and calculate the steric number of this oxygen. So that's number of sigma bonds. So here's a single bond, so that's a sigma bond. And then here's another one. So I have 2 sigma bonds, so 2 plus number of lone pairs of electrons around the atom. So here's a lone pair of electrons, and here's a lone pair of electrons. So I have 2 lone pairs of electrons. So 2 plus 2 gives me a steric number of 4. So I need 4 hybridized orbitals for this oxygen. And we know that occurs when you have sp3 hybridization. So therefore, this oxygen is sp3 hybridized. There are 4 sp3 hybrid orbitals around that oxygen. All right, let's do geometry of this oxygen. So the electron groups, right, there are 4 electron groups around that oxygen. So each electron group is in an sp3 hybridized orbital. The geometry of those electron groups might be tetrahedral, but not the geometry around the oxygen here. So the geometry around the oxygen, right, if you ignore the lone pairs of electrons, right, you can see that it is bent. Right? So even though that oxygen is sp3 hybridized, its geometry is not tetrahedral. The geometry of that oxygen there is bent or angular. All right, and because of symmetry, right, this carbon right here is the same as this carbon, so it's also sp3 hybridized, and then this carbon over here is the same as this carbon, so it's also sp3 hybridized. So symmetry made our lives easy on this one. All right, let's do one more example. So once again, our goal is to find the hybridization states and the geometries for all the atoms except for hydrogen. And so once again, let's start with carbon. Let's start with this carbon right here. All right, so once again, our goal is to find the hybridization state. So the fast way of doing it is to notice that there's one double bond to that carbon, so it must be sp2 hybridized, and therefore the geometry is trigonal planar. Right, so trigonal planar geometry. All right, let's do the steric number way. So if I were to calculate the steric number, right, steric number is equal to number of sigma bonds. So here's a sigma bond. Here's a sigma bond. I have a double bond between the carbon and the oxygen. So one of those is a sigma bond, right, and one of those is a pi bond, which I'll draw in red here. So I have 3 sigma bonds around that carbon. So 3 plus 0 lone pairs of electrons gives me a steric number of 3, so I need 3 hybridized orbitals, and so once again sp2 hybridization. All right, let's do the next carbon. So let's move on to this one. All right, so I see only single bonds around that carbon. Therefore, it must be sp3 hybridized with tetrahedral geometry. So sp3 hybridized tetrahedral geometry. Same thing for this carbon, right? Only single bonds around it, only sigma bonds. So it's sp3 hybridized with tetrahedral geometry. Let's finally look at this nitrogen here. Right? So if I want to find the hybridization state of this nitrogen, I could use steric number. Right? So the steric number is equal to number of sigma bonds. So around this nitrogen, here's a sigma bond. It's a single bond. Right? Here's another one, and here's another one. So I have 3 sigma bonds. I have 1 lone pair of electrons. Right, so 3 plus 1 gives me 4. A steric number of 4 means I need 4 hybridized orbitals, and that's our situation with sp3 hybridization. And so this nitrogen is sp3 hybridized. But its geometry is not tetrahedral. Right, so the geometry for that nitrogen, as we discussed in an earlier video, right, so it has these 3 sigma bonds like this and a lone pair of electrons, and that lone pair of electrons is at an sp3 hybridized orbital. And if we look at that geometry, right, and ignore the lone pair of electrons, because you always ignore the lone pairs of electrons when you're looking at geometry, we can see we have this sort of shape here. So the nitrogen's bonded to 3 atoms, the carbon, hydrogen, and hydrogen. And then we have this sort of a shape like that, right? So in the back there. And you can see we call this trigonal pyramidal, right? So the geometry around that nitrogen is trigonal pyramidal. All right, so that does it for 3 examples of organic hybridization. So practice a lot for this.